Okay, guys, in our last class, we discussed the velocity of a particle in a simple harmonic motion. Let's say is the center of the simple harmonic motion. Amplitude A, the amplitude is the maximum displacement measured from the center. And so if we consider this side is positive, then this side is negative. So here this amplitude will be minus A. So a particle moving between oscillating between plus A and minus A. So its velocity, instantaneous velocity, related the relation between the displacement is given by the following formula. V equals, I write the square of that. V squared equals omega squared times A squared minus H squared. So this gives the velocity of the particle at any given displacement. Okay, so this is the formula. So we discussed this in our last class. By the way, there are some new students joined to today's session. Can you text me your batch, like 2025 or 26? Can you let me know in the chat box? Okay, so there are students from three different batch, 2025, 26, and 27. By the way, this class is ideal for 2026 and 25 students, but there is one student joined from 2027. Normally, to understand the other units, they have to finish the unit 1 and the mechanics, unit 2. Normally, my class goes like I will be doing from beginning, from unit 1, I will finish the mechanics. Once I finish the mechanics, the unit 3 and electronics goes parallel. So while I'm doing unit 3, I will be doing electronics and mechanical properties of matter and radiation. Those parts I will parallelly do, and I will finish the syllabus within 1 year. So it's not within 1 year, it's something like 1 year and 2 months. Okay. So anyway, so coming Sunday, I'll be starting 2027 batch time 11 a.m. Okay. All right. So that student who has joined through joined from 27 batch, this is we are at the middle of unit 3. Okay. So this session is for 25, 26 batch students. But then again, if you want to get some idea, you can stay. If you don't understand, it's totally fine. Yeah, I'll continue. So this formula gives the velocity of the particle at given any instant, given at any displacement. Okay. So from this formula, we can find if x equals to 0, if x equals 0, right? You can see now here v squared is equals to omega squared times a squared minus x squared. So if this omega is constant for a given oscillation, given simple harmonic motion, omega is constant. Okay, because omega is, we know omega equals k over m square root. So k is being constant, m mass of the particle. So this thing is constant for a given simple harmonic motion. Therefore, omega is constant. Okay, and a is also constant for a given simple harmonic motion. Amplitude, the maximum displacement amplitude is also constant. But so therefore, this velocity varies with x. If x is increasing, you are subtract, right? If x increases, this value is decreases, so overall value decreases, therefore velocity decreases. Okay. To have a maximum velocity, x has to be minimum. The displacement x has to be minimum. So the minimum value is x equals 0 when the particle is at the center. Uh, x is minimum, right? So if x equals 0, v will be v max. V will be maximum velocity. So I say v equals to v max. So then v max is given by, so here this 0. So v max squared is equals to a squared omega squared. Okay. So therefore v max equals to plus or minus a omega. You are taking the square root both sides. So you get plus a omega and minus a omega. So this is the maximum velocity. If you want only the magnitude, you can write v max is equals to a omega. I'll explain you why we get two solutions here, mathematically as well as conceptually. So mathematically, when we solve a formula, for example, uh, x squared, let's say equals to 4. How do we solve this? X squared equals to 2 squared. Take this to this side. X squared minus 2 squared is equal to 0. X minus 2 times x plus 2 equal to 0. The product is equal to 0. Therefore, x minus 2 equals 0 or x plus 2 equals 0. Therefore, you get two solutions, x equals 2 or x equals minus 2. Right? So when you take the square root of this, here have 2. So x equals 2, x equals minus 2. So this you have already studied in your O levels, right? The solutions for equations, solving quadratic equations that you have done. All right. So that is mathematical reasoning. Okay. So likewise, when you solve this, you get two solutions, plus a omega and minus a omega. So the physically, what is this means actually, when x equals 0, there can be two solutions. One is particle is moving this side. So if this moving this side, right? So the particle goes from here to here and then again returns back and then comes here, again moves here. So it will oscillate between plus and minus a. So when the particle is moving this direction, let's say this direction is considered as positive direction. Then when the particle is moving this direction, it's negative. So we know velocity is a vector quantity, so it has both magnitude as well as a direction. So if that is positive in this direction is negative. So therefore we have two solutions, plus a omega and minus a omega. All right. So this gives the maximum velocity. And the minimum velocity is, we know when x is maximum. When x is maximum, the velocity will be minimum. So that is x equals to a. When you put x equals a, v will be 0. So that means at the amplitudes, the displacement are 0. Now, for example, you can take a small pendulum, give a small displacement and drop. What happens is oscillate here and here, but at the amplitude, it instantaneously velocity is 0. At here, velocity is 0, and again, velocity increases, maximum again decreases, 0 increases, like okay, right. So these things we discussed in the last class, and also we plot the graph of velocity, how the velocity varies with displacement. All right. Those who are not there in the last class, you can take some time. You can note down this. Take a screenshot and write. All right. So the next we want to plot the graph of velocity versus displacement. So the formula is, we know v squared is equals to omega squared a squared minus x squared. So I'll expand this formula. V squared is equals to omega squared a squared minus omega squared x squared. I take this term to the other side. V squared plus omega squared x squared is equals to omega squared a squared. Okay. So then what I'm going to do is I will be dividing both side by omega squared a squared. So then here I can separately divide v squared divided by omega squared a squared plus omega squared x squared divided by omega squared x squared. So this omega squared cancel. Inside it will be 1. Okay. So then I have v squared over omega a squared plus x squared over a squared is equals to 1. So this is actually, so this derivation is not there in the syllabus, but I just did for to give some impression about this. Okay. And here this equation is actually the equation of ellipse. If you have this function x squared over a squared plus y squared over b squared is equals to 1. This is the equation of ellipse. Equation of ellipse. Okay. So you have coordinate axis xy plane x y. Okay. So here x plus a and minus a, y plus b minus b. So then it is a ellipse. So it has to be elliptical shape. The up and down both has to be same height. Okay, so if you draw like this, it will be wrong. This cannot be pointed. It has to be like when you draw y equals a stuff, you parabolic graphs in O level, to take a curve shape. No, likewise, it has to be there. It shouldn't be pointed like this. It is wrong. It is not elliptical shape. This is the elliptical shape. Okay. So in this equation, what if a equals to b? If a equals to b, let's say a equals b equals simple r. Now what do you get? Here you get x squared plus y squared, r squared, r squared. So r squared is common and take as a function equals 1. R squared to the other side, x squared plus y squared is equals to r squared. So this is the equation of a circle. So if the this not stretched, you can see this side is little stretched than this side. So you get a elliptical shape. But both having the same uh, horizontal vertical, then you will get a circle. Okay. If a equals to b, then it will be a circle. Anyway, these things not there in the physics syllabus. Just to give you some idea about how this graph comes. Okay. So then this is, you can see this is the equation of an ellipse. So I have x axis and y axis, v x. So x plus a, the range of x is plus a and minus a. Okay. Here plus a minus a, b is plus a omega and minus a omega, minus a omega. So now let's plot the relation. So it's elliptical curve. So it has to be symmetric both side. Yeah. So this is the graph how velocity of the particle in a simple harmonic motion changes with its displacement measured from the center. You can draw this. This part is not necessary. If you want, you can write down the this graph. You should know to plot this graph. In exam, you might get a question. Draw the graph of velocity versus displacement of a particle in a simple harmonic motion. Okay, now I'll give you a question. Draw the graph of momentum versus displacement, momentum versus displacement of a particle in a simple harmonic motion. Draw the graph of momentum versus displacement of a particle in a simple harmonic motion. Okay, draw this. Each of you has to draw this and send me to the chat. Okay, I want to view your answers. Okay, send me your answers in the chat box, all three of you. Aida, are you finished? Can you share your answer? You can take a snap and send it to the chat. Okay. Miss Aida? Yeah, fine. You can send it in WhatsApp. What about Unisilla? Finish? Okay, all right. So the momentum of the particle, momentum is, we know, is given by P equals mv. Since the mass is constant, mass of the particle is constant, P is proportional to V. So therefore, the momentum has the same variation as the velocity. Okay? Momentum has the same variation of velocity. So we write the momentum here, P equals to mass times velocity is omega a square minus x square square root. So then if we plot the graph, we have momentum and this displacement. Displacement, the range is a and minus a. So the momentum is so a omega multiplied by mass times velocity. So here you put c equals 0, then you get p equals plus or minus m omega a. So m omega a minus m omega a. So we have the graph. So if I draw like this, it's wrong. It shouldn't be point, it has to be So this is the graph. So the same variation, but this value only will change here. A omega velocity, the momentum, you multiply the mass, so you get the corresponding values here. Okay. Yeah. So this is also a ellipse, right? So we have momentum of the particle given by mass times velocity. Momentum of the particle is given by mass times velocity. Since the mass is constant, momentum is directly proportional to the velocity. That means if velocity increases, momentum also increases. If velocity decreases, momentum also decreases. So it's directly proportional. The same variation will be there for momentum. Okay. So the same variation will be there. Okay. So here P equals m times V. For V, you can substitute here because V is equals to, we know, V equals omega times a square minus x squared square root. So I have substitute here, so you get the momentum in omega times a square minus x square. If you put x equals 0, you get plus or minus m a omega. So here plus m omega a minus omega a. Okay. So you get again a elliptical shape, right? Okay, is it clear? All right. So quickly draw this. Okay, and then let's write the topic. Kinetic energy, potential energy, and total energy of a particle in a simple harmonic motion. Kinetic energy, potential energy, and total energy of a particle in a simple harmonic motion. Okay. So the kinetic energy is, we know, is given by kinetic energy EK is equals to half mv square, half mv square. Okay. So the kinetic energy is given by half mv square, and then potential energy EP is given by the elastic potential energy. When spring, if it's a spring, the particle is attached to a spring, so the elastic potential energy half k x squared. So this is the kinetic energy. And this is potential energy. Okay. And then total energy. We know the total energy is the sum of kinetic energy and potential energy. Total energy is equals to kinetic energy plus potential energy. Okay, so total energy I write ET, E total. Kinetic energy is half mv square plus potential energy is half kx square. Okay. So here we have two variables v and x. So therefore, what I'm going to do is, I know how v changes with x. So therefore, I can substitute that for here. Total half m v squared is equals to omega squared a squared minus x squared plus half kx squared. So now I can expand the bracket and simplify. E total is equals to half m omega squared a squared. Okay. And then half minus m omega squared half m omega squared x squared plus the kx squared. We know omega is equals to k over m square root. So therefore k equals m omega squared. You square this term and multiply m here, you will get this. So I can put that here. So half m omega squared x squared. So you can see minus m omega squared x squared plus m omega squared x squared cancel. So we get the total energy half m omega squared a squared. So this is the total energy of the particle in a simple harmonic motion. Okay. Now tell me the total energy of the particle, total energy of a particle in simple harmonic motion depends on what factors? Okay. So the question is the total, what are the factors that affects the total energy of a particle in a simple harmonic motion? Okay. Put your answers in the chat box. What are the factors that affect the total energy of the particle in simple harmonic motion? You can type it and send in the chat box. You can type all the factors that you think it will affect the uh, simple harmonic motion, and then you can text. Okay. So you in a one message you drop all this. Yeah, I'm not getting any answers from Nisula. Okay, so I got two answers. I mean, I got the same answer from both of you: amplitude and angular velocity. Okay, so from these, amplitude, yes, it is correct. Angular velocity, no, it's not. The energy of a simple harmonic motion only depends on amplitude, not angular velocity, not mass. So you can see mass here, not mass. So I will write the vectors, mass of the particle, and then we have frequency and periodic time. Okay, so mass of the particle, no. Frequency, no. Periodic time, no. So only amplitude is the quantity that affects the energy of a simple harmonic motion. I think one year MCQ they have been asked that. Okay. Now you may wonder, so why it is not omega and m? Because m omega squared is actually m omega squared is equals to k, spring constant. So in fact, the total energy is given by half k a squared. So here, if you change the mass, if you increase the mass, omega will decrease, keeping that k constant, because k, the name itself, it's a spring constant. For a given simple harmonic motion, k is a constant. Okay. So therefore, the energy of simple harmonic motion depends on only on its amplitude, not on the mass, not on the periodic time, not on the frequency. Okay. So now, for example, let's say there is a pendulum. First, you give a small displacement, then it will have some energy E1. Now, next time you give a large amplitude, so then it will have an energy E2. So definitely E2 will be greater than the E1. Okay. So the amplitude. So energy of a simple harmonic motion is in fact proportional to E total proportional to amplitude square. Okay. That is very important thing that you should note down. The energy of a simple harmonic motion is directly proportional to the square of the amplitude. Write in words. First write down this. Okay. After that you can write the energy of a particle in simple harmonic motion is directly proportional to the square of the amplitude. So this relation is not only true for particles, okay, this is also true for fields, electric field. Now, for example, if you take electromagnetic waves, they have vibrating electric fields. So this electromagnetic waves energy also directly proportional to its amplitude squared. Okay. It's better you write like this as I wrote periodic time, write each factors and put from. So then you will know, okay, so it only depends on amplitude. Okay. So we have the energy of a particle in simple harmonic motion depends, it's directly proportional. Energy of a particle in simple harmonic motion is directly proportional to the square of its amplitude. All right. So now we know the kinetic energy and then potential energy and the total energy. Okay. So here this is the maximum kinetic energy. I will explain you this is the maximum kinetic energy, this is the maximum potential energy. The maximum kinetic energy is equals to the maximum potential energy and it is equals to the total energy. That will be clear once we draw the graph of kinetic energy, potential energy and total energy. So the next topic under this subtopic, write down the graph of the variation of kinetic energy, potential energy and total energy of a particle in simple harmonic motion with its displacement. So write down the subtopic, variation of kinetic energy, potential energy and total energy of a particle in a simple harmonic motion with its displacement. So variation of these things with its displacement. Okay, I give you 3 minutes. You had to draw all the three graphs in the same graph. Okay, it means one axis, one coordinate system. You have to draw. So this is displacement, and this one you can say energy. So in energy, that's got total energy how it varies, kinetic energy how it varies, and potential energy how it varies. Start. So here also for a given simple harmonic motion, the total energy is constant, right? If A is constant, total energy is constant. So you write down that. So total energy is the constant. Okay. After this, you wrote one sentence, right? Energy is proportional to amplitude squared. So right, and there you write if the amplitude is constant, total energy is constant. Okay, so first I'll start with potential energy. So potential energy with displacement, that is half mx squared. So it's like y equals uh, half mx squared, or you can say half y equals ax squared, where a is the half k. So y equals ax squared. So this graph you have drawn in grade 10 classes, and I will mark the range here as a and minus a. So it is so parabolic shape, parabola. It has to be symmetric both sides. Then so that is potential energy. And we want the relation kinetic energy versus displacement. So the kinetic energy is given by E k equals half m v squared. Half m v squared is equals to a squared minus x squared. Before that, let's consider the total energy. The total energy E total is equals half k a squared. So that is a constant. Okay. So now here potential energy, if you put x equals a, you get half k a squared, and the total energy is constant. This is the potential energy EP. So the total energy half k a squared. Okay, it's a constant. So this is total energy E. So you can see. Okay, and let's plot the kinetic energy graph as well. So here it will be E k equals half m a squared minus half m x squared. So E k is equals to minus half m x squared plus half m a squared. Sorry, here v squared is there is omega should be the omega squared a squared minus omega squared a squared and omega squared squared. So minus m omega squared squared plus half m omega squared a squared. So this is has y equals minus ax squared plus this constant plus b. So it's a parabolic graph with maximum, and that maximum value is b. Okay, so it will be like this. So this graph you have always. So this is the graph. So this is kinetic energy ek. So you can see the kinetic energy is maximum at the center at 0. Okay, so at the center kinetic energy is maximum and the potential energy is 0, because At the center, the spring, if you consider spring particle system, spring is in natural length, so it is not under compression or tension. So there is no potential energy, elastic potential energy. Okay, so that you can see the total energy is the maximum kinetic energy. So at x equals 0, E P equal to 0, E K kinetic energy is half m v squared. V is a squared omega squared, at omega squared a squared. Okay, E K is half m omega squared. Therefore, E total is, we can say, E total EP plus EK. EP is 0, so that is equals to EK. The total energy is equal to the kinetic energy. And at x equals plus or minus a, you can put either plus a or minus a, you will get EK is 0, kinetic energy is 0, and EP, the potential energy, will be half k x squared. For the x, you substitute minus a or plus a, you get, if you put minus a also, if you square it to plus a only, you get. And that is equals to E total is equals to EK plus EP. EP is 0, so there E total is equals to EP, right? So you can see here the total energy is equals to the potential energy, kinetic energy is 0. And now these two are actually the same equations, because K equals m omega square. K is actually equals to m omega square. Substitute, you get this. Okay, right. So you can plot this graph, and you can see there are two occasions where the kinetic energy is equals to the potential energy. Now, if you draw any line on this, any vertical line, okay, the sum of this, let's say simple A, and this one simple B, A plus B is always equals to this height C, the total energy. So kinetic, any instant, the potential energy plus kinetic energy is equals to total energy. So then this two has to be the same, no? Right? Because this is at the middle, this length is equal to this length. Kinetic energy plus potential energy, so it is doubles, gives the total energy. So here also the sum is here uh, total kinetic energy plus 0 is equal to total energy. Okay. So plot this graph. If you have any questions regarding this, please ask it now. Which part you didn't understand? The graph, how to plot the graph, or getting these equations? What? Equation. So this kinetic energy is straightforward. No, sorry, potential energy half kx squared. So that is y equals mx, y equals ax squared type of graph. You have drawn in your O grade 10, y equals 2x squared, y equals half x squared, y equals minus half x squared, y equals minus 1 over 3x squared. These graphs you have done in your O, right? So if the coefficient is plus, you get a minimum. Coefficient is plus, you get a minimum. and that minimum's value is 0, x equals 0. So when x equals 0, minimum value y will be equal to 0, right? And kinetic energy half mv squared. Okay, v squared is equals to omega squared a squared minus x squared, and then you multiply this with this. Okay, so you get this into this in plus into minus half omega squared x squared. To take this term here, මේ term එක මෙතනට අරන් මේ term එක. So then you have y equals minus, so this is a constant, right? Constant times x squared plus another constant. So y equals minus ax squared plus b. So these type of graphs also you have done in grade 10 oral maths. Oral maths grade 10. So then here you have maximum, because negative coefficient is negative, maximum, that maximum value is equals to b. So the maximum value is equals to m omega squared a squared. So this maximum value is what? Half k a squared. K is m omega squared. So this maximum value is half k a squared. Did you understand now? Okay, great. So quickly draw this, and you should emphasize that if you take any point and draw a vertical line, okay, then the sum of kinetic energy, here the value, let's say a, this value b, so a plus b is always equals to the total energy half k a square. Okay, this value a, this value b, a b, a plus b is equals to this. See here, if you take this length b, you need this much, that much is here. That is true, you can draw anywhere in this. Okay, so here you should know total energy is constant, and total energy is always the sum of kinetic energy and potential energy. Okay, and at the x equals 0, kinetic energy is maximum and potential energy is 0. Okay, that maximum value is equals to total energy. And at amplitudes, either plus a or minus a, the kinetic energy is 0 because the particle becomes instantaneous, instantaneously rest. The velocity becomes 0 at the amplitudes. When you oscillate, okay, when you take a pendulum and oscillate, what will happen? It will oscillate like this, no? So here suddenly it becomes 0 and only turns back. Okay, so at the amplitudes, the velocity becomes 0. So that kinetic energy is 0. So kinetic energy will be 0. Potential energy maximum, because the spring will be maximum extension. Okay. Okay, so write down this question. Write down this question. Uh, find the displacement of a particle in find the displacement particle in single. Yeah, you write Find the displacement of a particle. Find the displacement of a particle in simple harmonic motion at which find the displacement of the particle in simple harmonic motion at which its kinetic energy is equals to potential energy. Kinetic energy is equals to its potential energy. Also, find the corresponding kinetic and potential energy values. Also, find the corresponding kinetic and potential energy values. Okay, I'll give you 3 minutes to come up with an answer. All right. You got the answers for that? So we want to find the displacement at which the kinetic energy is equals to potential energy. So it's simply EP is equals to EK. The potential energy is half kx squared. Kinetic energy is half mv squared. So we want to find x. So half and half answer. Kx squared is equals to m times v squared is, we know, omega squared a squared minus x squared. So we know m omega squared is actually k. K equals m omega squared. We can cancel for x squared is equals to a squared minus x squared. Take the other side. 2x squared is equals to a squared. Take the 2 to the other side. X squared is equals to a squared over 2. So we have x equals a squared over 2 square root. So x equals plus or minus a over root 2. So we have two solutions. One is plus a over root 2. So here you can see the kinetic energy is equals to potential energy. Kinetic energy is equals to potential energy. The other solution is minus a over root 2. Okay. So we have two solutions for the given question. There are two locations, two positions where the kinetic energy is equals to the potential energy. Okay. And also then we want to find the corresponding kinetic energy and potential energy. So now we know x equals to a over root 2 either plus or minus. So then we have the corresponding potential energy EP equals half k x squared. X equals a over root 2 squared. So therefore EP equals to 1 over 2 times k a squared over root 2. If you square it, it will be 2. So EP equals to 1 over 4 k a squared. And you need to find the kinetic energy. And you can start with this equation and v squared. You can substitute a squared minus omega squared a squared minus squared, and you simplify and get a value. But it's not necessary here, right? Because kinetic energy is equal to potential energy. So if you do that, you will get that same value for this 1 over 4 Ka squared. So then if you add these to 1 over 4 Ka squared, 1 over 4 Ka squared, then you get half Ka squared, which is the total energy of Ka squared. Okay. Second question, next question. Find the kinetic energy and the potential energy of a particle in simple harmonic motion. Find the kinetic energy and potential energy of a particle in simple harmonic motion at a displacement of a over 2. That means amplitude divided by 2, or displacement of half amplitude, 1 over 2a, half the amplitude. Okay. So at half the amplitude, find its kinetic energy and potential energy, and try to compare the values. Try to, once you get the values, compare which is greater and which is smaller. Mhm. Okay, let me check. Okay, so we want to find the kinetic energy and potential energy at x equals a over 2. It's just a substitution. Okay. So first we can find the potential energy. EP is half a x squared. So at x equals a over 2. So EP is equals to half k. A is x is a over 2 whole thing squared. So for EP equals 1 over 8 k a squared. Very good. And then we want to find the kinetic energy Ek. That's half mv squared. And we know the v is given by omega, v squared is given by omega squared a squared minus x squared. So Ek is equals to half m omega squared is k a squared minus x is a over 2 squared. So then we have kinetic energy is equals to half k a squared minus here a squared over 4. So therefore Ek equals, here we can take the common denominator 4 and it is can take out. So 1 over 2 into 4 8 k. Now here 4a squared minus a squared. 4a squared minus a squared is 3a squared. So Ek equals 3 over 8 k a squared. Okay. So it is clear that kinetic energy is greater than the potential energy, right? So kinetic energy is greater than potential energy at x equals a over 2. It is either plus a or minus a over 2. See, a over 2, this a over root 2, a over 2 is somewhere here. Okay, because root 2 is smaller than 2, so dividing by big number, value is smaller. Here, half is here. So at a over 2, okay, the kinetic energy is greater than the potential energy. This side also you can see kinetic energy is greater than the potential energy. Okay, and if we add these two, you should get half k squared. So if we add this 1 over 8 and 3 over 8, 4 over 8, so 4 over 8 is 1 half. 4 over 8 is 1 half, so we get the total energy same value of ka squared. Okay, one last question. Write down the kinetic energy of a particle in simple harmonic motion. The kinetic energy of a particle in simple harmonic motion the kinetic energy of a particle in simple harmonic motion is 2 times its potential energy. The kinetic energy of a particle in simple harmonic motion is 2 times its potential energy at a certain displacement. At a certain displacement, full stop, find this displacement at a certain displacement and full stop, and write find this displacement. So the kinetic energy is 2 times its potential energy, and then you have to find the corresponding value. By the way, here in the previous one, actually at half a displacement, the kinetic energy is 3 times its potential energy. So you can if you want, you can put a note, that's fine, right? So here at the half the displacement, kinetic energy is 3 times its potential energy, right? So you can write, because these things will be important. These small points will be important when you are trying to answer for MCQ question. They will might ask that truth or they'll give 4 sentences out of this which are true. So they will say at the half the displacement, the kinetic energy is 2 times the potential energy. So if you know it is 3 times, then you know it's wrong. Otherwise, you have to check. Right? It will consume your time. That's why you have to study each and every little thing perfectly. කරන දේ හරියටම කරගෙන ගියා නම් කිසිම දෙයක්. So to do that, what you have to do, again and again revise your note completely. මොනවා හරි අමතක වෙනවා. මතක හිටින් නැත්නම් ඒක ආයෙ ආයෙ නැවත නැවත බලන්න. You have to study that again and again so that you should not miss any single note. Okay. Okay, so my question is, so at a certain displacement, the kinetic energy is 2 times its potential energy, and you need to find that position, that displacement. අනිවාර්යෙන් note එකේ දාගන්න that the half the displacement, the kinetic energy is 3 times the potential energy. Share your answer if you got the answer. Ah, okay, so I got an answer. It's equal to a over root 3 plus or minus a over root. Yes. By the way, so normally in my theory class, I ask you to draw the velocity time graph, velocity versus displacement. So after that, we do the energy, and then I'll ask students to draw this graph. Some students will draw the energy graph, like for energy and displacement. For kinetic energy, they will draw like this. Energy never can be negative. Okay, so that's the mistake I have noticed when I'm doing a class. Okay. So it is always should be like. All right. So here we have the kinetic energy is 2 times the potential energy. So kinetic energy is half mv squared is equals 2 times half k x squared. Half and half cancel. Mv squared is, I can write, omega squared a squared minus squared is equals to 2 times kx squared. So k is equals to m omega squared. Cancel. So a squared is equals to minus x squared to first side plus x squared. So 2x squared plus squared. So 3x squared equals a squared. So therefore x squared is equals to a squared divided by 3. So x equals plus or minus a over root 3. So x equals plus or minus a over root 3. So the next one. Now here we plot the variation of kinetic energy, potential energy, and total energy with displacement. Okay. So it's with displacement. So displacement. So the next one, next topic, the variation of kinetic energy, potential energy, and total energy with time. Plot the graph, write the topic, the variation of kinetic energy, potential energy, and total energy of a particle in simple harmonic motion with time. I'll give you a minute. Okay. So here we want to plot energy versus time. We know the total energy remains constant. Total energy will remain constant. So let's say the total energy that remains won't change. And then let's say at t equals 0, the particle is center. Because in some cases you can consider the particle start from or here, but we consider if it's in center. So if the particle is starting in center, the kinetic energy is maximum, and then it, at amplitude it goes to 0. Then again it will, So this is actually sine graph. You draw the sine graph from here, up and down. So this will be not actually the sine graph, it is the square of sine graph. So the time here is, let's say, t over 4. And this time, here the time is t over 2, half the period time. And this will be 3t over 4. And this is one complete cycle. And here this will be one cycle, periodic time t, this pi t over. So this kinetic energy, E k, and this is total energy, E t, and the potential energy will be the other way around. This is kinetic energy, and this is potential. So this is the variation of kinetic and potential, total energy with time. The total energy remains the, and here the sum of kinetic and potential is equals to total energy. If you take, draw this. So here t equals 0, the particle is at the center. You had to mention that. You can just illustrate this, or you can write at t equals 0, the particle is at center. Okay. So here the total energy is constant. Okay. Now I can't explain you how this variation comes. Actually, we know kinetic energy K is equals to half m. Sorry, kinetic I'll take potential energy is equals to half kx square. So this is the variation of with this place. We want to get the time, to get the relation between displacement and time. We want to study our next topic, which is the equivalence circular motion with simple harmonic motion. There we will be able to get an expression for x equals to a sine omega t. So we plug that here. So et equals to half k a kx square. So x is a sine omega t squared. Therefore, potential energy is half k a squared times sine squared omega t. So this is the total energy. So therefore, EP equals E total times sine squared omega t. So this is constant, that value is E total. E is here. So this is the E total value, which is half Ka squared. So E total, that is equal to half Ka squared. And from that you have a sine squared graph, okay, for potential energy. Uh, A, A, and now this is the potential energy. Yeah, so here this graph. So the maximum value is E total, and from that you have square of sine graph. Okay. So the potential energy you will get like the square of sine graph, and then here half the period. That means the particle from 0 to it will go, and then again another half a period, another half a period, and then the complete one period. So within a period, the potential energy varies like, okay. And then the kinetic energy. So for you in your syllabus, you have only this graph. They want to ask how this comes. Okay. This relation and all, no need to explain. So kinetic energy, we have Ek is equals to half mv squared. So Ek equals half m. V squared is actually omega squared a squared minus x squared. So then Ek equals half m omega squared a squared minus half m omega squared x squared. So this is actually total energy. So Ek is E total minus, so m omega squared is k, half k, okay. X squared is again a sine omega t, this a sine omega t squared. So Ek equals Et minus half k square of a is a squared sine squared omega t. So then half k is again total energy. So you have E minus E total sine squared omega t plus E. So then if I try to draw this one, this actually the same graph, this Et sine squared omega t, right? Et sine squared omega t, this graph will be drawn in this direction. Okay, the mirror image, to keep a mirror, the mirror image of this, just to take this multiplying by minus that you have studied in your O level. O level you have studied y equals ax squared graph will be like this. Then if you take y equals, for example, 2x squared, then minus 2x squared graph will be the mirror image of, right? So this part will be the mirror image of this, and then you have to add et. You take the mirror image and shift by et. So you this graph you get here. So you get this. By the way, in your level you don't have to know these things in detail. Only thing you should know the total energy with time, how it varies, kinetic energy and potential energy, the variation how it will be when the particles start from here, and also if the particles from here, then the kinetic energy and potential energy will change. The particle time will start from here. Okay, so those are the important things that you should know. Not all. Okay. So I'll give you as a question, starting taking the particle here, draw the variation of total energy, potential energy, and kinetic energy. Uh, so So this equation that we will study in our next topic, that is for every simple harmonic motion, there is a corresponding circular motion. By understanding that circular motion, we can derive this equation. This equation is there in our syllabus. Okay. So, but this derivation for this graph, those things are not there. You should only know the variation. Write down this question. Draw the variation of kinetic energy, potential energy, and total energy of a particle in simple harmonic motion with time. Of a particle in simple harmonic motion with time if if time is measured from one of its amplitudes. So unlike the center, now you measure the time either one of the amplitudes. Okay. So try to plot the graph. Living in your Okay, I believe you have drawn the graph correctly. So we draw it correctly. The total energy won't change. Only thing I have to change is, so now I'm starting from measuring the time from amplitude. You can take either plus amplitude. So at the amplitude, the kinetic energy is 0. So this curve will be the kinetic energy now. Ek. And the potential energy will be maximum. So this is EP. So if you change the two curves labeling, change that, that will be the correct answer. All right. So let's move on to the next topic. The correct graph I explained you just have to take the same graph and change the kinetic energy and potential energy. Okay. In the previous one, kinetic energy start from the maximum value because you start from the center. But in this graph, kinetic energy start from the zero because the particle is at the amplitude initial. The only thing you change the curves of EP and EK, kinetic energy and potential energy. Okay. All right. Uh, by the way, Aida, can you do me a favor? After the class is over, is it possible for you to share the note? Because there is one student who to join, is not there. She asked for the note as well. If possible, otherwise, you get the. You can share the note. Share it to me personally. Okay. Yeah, if you do so, I can check whether you have done the questions correctly and if there's anything lacking in your notes. All right, so let's write down the next topic: relation between circular motion and simple relation between T and N. Okay. So for this, let us take a screen here. This screen, a white screen, and here particle is moving in a circular path in vertical plane. So particle is moving in a circular path in vertical plane. That means now if I take a stone attached to a string, if I rotate like this, it will rotate in a horizontal plane. So I'm rotating like this. So it is going in a vertical plane. And there is a screen this side. Okay. And then I'm projecting a parallel beam of light. So parallel beam of light. So I consider at t equals 0, the particle is here. But after some time, the particle is now moved to here. So some general time t equals 30. O is the center of the circular path. And I draw a horizontal line, the same O. I take this point O dash. And let's consider the radius of this circle to be uh, capital A. A is the radius. So if I take this, so here this will be plus A, and here it will be minus A. Okay. So uh, the particle is moving in this circular path, then we can see its shadow is going between A and minus A. It is actually oscillating between A and minus A. Because here you can see the particle, let's say, has a constant angular velocity omega. The particle is moving with constant angular velocity omega. And then let's say the tangential velocity here v, and that v is given by, you have studied in rotation motion. For example, v equals r omega, radius into omega, right? So here the radius is a, therefore v equals a omega. Okay. So here we have tangential velocity v, that is equals to a omega. So the particle, its shadow is also here, it has the velocity here, a omega. But when the particle comes here, it doesn't have a velocity in this direction, because velocity is completely in this direction v. Okay, there is no component in this direction, so here the velocity will be 0. Okay, and then again the particle comes here. Here the velocity is downward a omega, so the maximum velocity here a omega. And again when the particle comes here, the velocity in the downward direction will be 0, or the vertical direction is 0. Okay, because there is no component, that's perpendicular. Okay? So this shadow of the this particle shadow here going a simple harmonic motion. So we have equivalent motion. So this rotation motion and its vertical, we consider vertical component here, shadow projection, vertical projection is going a simple harmonic motion. Okay, are you all clear? So after some time t, the angular displacement theta, and the corresponding displacement, let's say, is x. Particle has displacement. Okay, so quickly draw this. Okay, so let us write. Let us consider a particle, a particle P, a particle. Let us consider a particle is moving in a circular path. Is moving in a circular path. Is moving in a circular path in vertical plane. In a vertical plane. In a vertical plane with a constant angular velocity. With a constant angular velocity. With a constant angular velocity omega. I didn't mention the radius. Circular path of radius a. Yeah, make it circular path of radius capital A. Circular path of radius capital A with a constant angular velocity omega. Okay, and then a parallel beam of light is incident. A parallel beam of light is incident on the particle a parallel beam of light incident on the particle that is parallel to the plane of the circular path. That is parallel to the plane of the circular path. Now, for example, if the particle is moving like this, I have to incident parallel to that plane. Okay. If I incident the light like this, won't happen. If I incident the light in this way, no. The particle is going in this plane, circular plane. The light has to be incident on it in a parallel to that plane. Okay. The light is incident on the particle that is parallel to the plane of circular uh, motion of circular path, and the shadow of the particle is observed in a white screen. On a white screen that is placed perpendicular to the light beam. Screen that is perpendicular to the light. Okay, and then separate it. Right? So we can say when the particle in circular motion makes a complete cycle. So you can see here when this goes here, this one is going here, then again comes here, comes here. So when this makes one cycle, this one makes one cycle, right? So the period time are same. Uh, yeah. So let's write down. Uh, when the particle in circular motion makes one cycle, then its shadow also makes one cycle on the screen. Makes one cycle on the screen. Therefore, the period time of the circular motion is equal to the period time of the simple harmonic motion. Therefore, the period time of a circular motion is equals to the period time of the simple harmonic. motion. So now, using this information, we can get an equation for the period time of the simple harmonic motion. So the period time of the simple harmonic motion is equal to period time of this circular motion. So period time of the circular motion we can find using uh, period time. Uh, yeah, theta equals omega t. We have studied this equation in rotation motion. Theta equals omega t plus half alpha t squared. Since it is moving at a constant velocity, theta equals omega t. So for one cycle, the angular displacement theta will be equals to 2 pi. So angular velocity omega to period time we denote by t. So therefore, period time is equals to 2 pi over omega. Okay. So this is how this equation has this equation equals to pi over pi down. Okay. So the next I can get the relation between x and the time. We know the radius is capital A, therefore this length was A. So this is x, therefore this one also x. So this is a right angle triangle. Okay. So the sine theta is equals to opposite x over A. So subject x, x equals A sine theta, and we know theta equals omega t. For any time theta equals omega t. Therefore, x equals A sine omega t. So you can use this formula to find the displacement after any time. Write down. So x equals A sine omega t. Here you should note that time is measured from the center. Yes, t equals 0 here, t equals 0 here. If the time is measured from here, then the formula will change to A cos omega t. Okay. Uh, that part I will explain later in a while. Okay. If you measure the time from here, t equals, sorry, x equals a sine omega t, either from here or here. Here or here means you are at here. Time t equals 0. But if you measure the time from here or here, you start to measure from either one of these places, then the formula change to a cos omega t. I will explain you how. But for the moment, you should know that a x is given by a sine omega t. Okay. So I'll give you a question. Write down this question. Um, yeah, write down. The amplitude of a particle in simple harmonic motion. Amplitude of a particle in simple harmonic motion is 1 meter. Is 1 meter. Mm. First up, mm, yeah, the amplitude of a particle in simple harmonic motion is 1 meter. First up, find the displacement of the particle. Find the displacement of the particle find the displacement of the particle after after mm, 3 hold on, mm, 3 t over 4. After 3 t over 4, if time is measured from center, if time is measured from center, full stop. Here capital T is the periodic time. Here capital T is the periodic time. Okay, it's a small substitution question. So get the answer. You just have to substitute here. So here you mention this formula is valid only if the time is start to measured from the center. Okay, you should write. Otherwise, you will forget. It should be there in your notes. This equation is valid if the time is measured from the center, when the particle is at the center of the simple harmonic motion. Okay, so that's the answer. So x equals a sine omega t. So x equals a is, I write a sine omega t. So x equals a is 1 meter sine omega into E is 3t over the time is omega T. So 3t over 4. Okay. And then x equals 1 meter times and period time is 2 pi over omega sine omega into 3 over 4 into 2 pi over omega. Omega and omega cancel. So x equals 1 meter times sine 3, 3 over 2 pi. So pi is 180. 180 into 180 divided by 2 is 90. 90 into 3 is 270. Sine 270, what is the value of sine 270? X equals 1 meter into sine 270. Hours and pounds. Okay, sine 0 is 1, 0, 1, minus 1, 0. No? So after 3 quarters, 1, 2, no, I think I'm making sine 3 over 2 pi. And let me know what is the value of sine 3 over 2 pi. So sine 180 divided by 2, 90, 90 into 50, 270. Sine 270 is, we know it is equal to sine 180 plus 90. So it's 180 is 90 into 2, even. Sign doesn't change. Sign remains sign. In the third quadrant, only the tan is plus, so it's minus. Minus sine 90. So sine 90 is 1. So minus sine 90 is 1. Minus 1 into minus 1. So x equals minus 1. So that means the particle start here, not in the plus direction. Here the particle will take horizontal. Let's A is 1 meter, is minus 1 meter. Particle will be here after that time. Okay, that's a small substitution question. Okay, write down another question. An object of mass, an object of mass uh, 0.5 kilogram, an object of mass 0.5 kilogram is attached to a spring with spring constant, a spring with spring constant 4 Newton, okay, 4 Newton per meter. A spring with spring constant 4 Newton meter undergoes a simple harmonic motion undergoes a simple harmonic motion. Hold on. An object of mass 0.5 kilogram is attached to a spring with constant 4 Newton per meter undergoes a simple harmonic motion. Uh, Hold on. Undergoes a simple harmonic motion. First up, object of mass 0.5 kilogram is attached to a spring with spring constant, undergoes a simple harmonic motion. It is observed. It is observed that the maximum velocity of this object, the maximum velocity of this object, maximum velocity of the object is 8 meters per is 8 meters per second. Okay. First up, find the displacement of the particle. Find the displacement of the particle find the displacement of the particle after 3 seconds. Find the displacement of the particle after 3 seconds. Alright. Current. Okay, you finish. So an object of mass 0.5 kilogram is attached to a spring of length 4 meter is undergoes simple harmonic motion. It is observed that the particle maximum velocity is 8 meters per second to stop and find the displacement of the particle after 3 seconds. Anyone finish? Okay, so let me do this. The formula is x equals a sine omega t. So we want to know omega and a in order to answer to this question. So omega, we know omega equals k over m square root. So omega equals k is 4 divided by m is 0.5. I should have given 1 point. So omega equals 8 square root. So is 2 root 2 ms, sorry, rad per second. That is omega. And then we want to find a. For that we can use, we have given the maximum velocity, V max is equals to a omega. So V max is 8 is equals to a is 2 root 2, yeah, it's 2 root 2 into the omega is 2 root 2, 2 root 2 into a. So therefore a equals again 2 root 2 meters, because this is actually square root of 8. If you divide this by square root of 8, you get square root of 8, that is again 2 root 2 meters. So therefore x equals, that is the amplitude of the simple harmonic motion. So x equals a sine omega t. So x equals a is 2 root 2 meters into sine omega is again 2 root 2 into 3. So x equals 2 root 2 into, you need to get this value, 2 into root 2 is 1.4, 141, 141, 441, square root 41. What is square root of 2? Is it 1.14? I think 0.141. Let me check if you have a calculator or if you know the value. This got confused. It is 414,141. 14 square root is 290. 190. 1.414. Yes. Thank you. So 1.41. That is 2 root 2. And then we have to multiply by. So 6 times 1.41. So we have 6 times 1 is 1. 6 times 4 is, so it's 0.1. Sorry, 0.6. 6 times 0.4 is 2.4. And 6.1 is 6. So 8.46. So sine 8.46. This is red, right? So you can use the calculator or can use the table. Okay. So then you get this value and multiply with this, you get the exact. Because this rad per second into seconds, 3 seconds. So you get in rad. If you want, you can convert this into the degrees. Those are fine. Okay. And then you can find the, okay, do that. All right. So we know the X formula is given by A sine omega t if is measured from when the particle is at the center. If the particle is somewhere here, okay, let's say particle is when it is here, we start to measure the time t equals 0. Okay. So corresponding this one will be here. So we have a initial angle. We take it as p. Okay. We had to draw this separately again, not in the same diagram. So I will redraw that, otherwise it's confused. So here you have, now it's starting t equals 0 here. So the part here t equals 0, and this is the amplitude a minus a, and this angle p. Okay. So then the particle is travels to here, let's say, after time t. So then the particle will be here. Okay. So then this is x. So this angle is theta. So then we have x equals, now this is a, radius a. Again, we can consider this x. So x equals a sine. Now the angle is theta plus p. Angle is theta plus p. So then now here we have x equals a sine. Theta is actually its angular displacement. The velocity is omega. So omega t. So theta equals omega t plus phi, where phi is the p is the initial phase angle. When you start to measure the time, initial phase. So called initial phase angle. Alarambaka form. Initial phase angle. Okay. Note down this. And after that, we have if if p is equals to pi over 2, 90 means equals to 9. That means you consider particle is starting from its amplitude. When it's here, particle here, p equals 0, right? If p is this, p equals 0, the particle is at the amplitude 0, here a, the particle is here, Then we measure the time. So then we get that formula is equal to a sine omega t plus t is pi over 2. Or you can write 9. So we have x equals a sine 90 plus omega t. We know sine 90 plus theta is cos theta. So a cos omega t. So if you measure the sine from here, the formula will be a cos omega t. So first you write down this. After that, you can write this part. Yeah, K means spring constant. So if you have initial angle, the total angle will be theta plus p. So x equals a sine theta plus p, where theta is the angular displacement due to the angular velocity. So that is then omega t plus. So p is known as initial phase. Okay. And if we are starting to measure from here, the particle is here in circular motion or here in simple harmonic motion here. Then the p is equals to 9, right? So then we can write, we interchange this 90 plus omega t. We know sine 90 plus theta is cos theta. So then sine 90 plus omega t is cos omega t. Therefore, it's equal to cos. Raise your hand if you're done right. Okay, you can take a screenshot. And do you have any questions from today's class? Is everything okay? All right, then. So that's all for today. And either if you can share the notes would be a great help. Oh, good. Okay, then. See you. Take care. Study well. See you, Manala.